Ladies and gentlemen, please welcome to the stage, Ashlee Breitner.
Good afternoon, everyone. If I can invite you all to find your seats to start this afternoon's breakout sessions. For those that don't know me, my name is Ashlee Breitner. I'm Workforce Director for the Electric Vehicle Center. All of you, I'm sure, are super excited to hear about the technology project updates forthcoming. So you, unfortunately, were not able to attend the concurrent workforce session. But I wanted to just take 1 minute to share with you a tremendous resource our team has been working really hard on over the last couple of years. We have developed an EV portal, that we call it, an EV workforce portal. This portal is really informed by industry for industry. So I want to make sure all of you as employers in the room, ecosystem partners are aware of this resource. We have a super short video we're going to share with you just to give you a quick introduction. And I invite you all to jump on the portal and see what resources are available.
The EV transition is underway, forging new paths for businesses and workers. But where do employers and workforce representatives find training and funding resources? Meet the EV Workforce Portal, your one-stop shop. Are you a large manufacturer looking for training opportunities? Check out the training directory. Small to medium-sized companies seeking to upskill your teams? Don't miss the funding database. Workforce professionals can explore the Workforce Resources section for the latest networks, tools, and reports. Add your own resources and keep the network up to date through the Contributor Portal. Train smarter, fund faster with the EV Workforce Portal. Visit evworkforce.umich.edu.
If anyone's interested in learning more about the portal, back at the EV Center table, just as you exit this room, our team is there. They have a demo video of it so you can see more details and specifics. But I encourage you all to check it out and utilize it as a resource. We're happy to answer any questions you have. I'm going to hand it back over to Jamie to get you on to the technology session this afternoon. Thank you.
And now, we're going to kick off our afternoon technology breakout session with Faye Zaski.
Thank you for that introduction song. I very much enjoyed that. I want to start off by thanking Alan for the opportunity to be up here today and share with you Toyota's story, how I feel that we are truly making headway in this EV space. And I think this morning we heard from General Motors, this afternoon we heard from Hyundai, and you can also see that those automakers are making significant progress as well. So my name is Faye Zaski. I'm one of the vice presidents of Toyota R&D. We are located here in Ann Arbor, Michigan. I have the joy of leading 3 functional areas, including materials engineering, prototype development, and performance evaluation. And that means that I get to work on EV vehicles every single day. That might be evaluating a battery cell or localizing a battery pack material, building a prototype vehicle. We build upwards of 6 vehicles a day on our small assembly line, or evaluating the performance of that EV vehicle. So with that, I'll click that green button and go next. All right, so today I wanted to excite you and tell you a little bit about what Toyota has been up to and some of the success that we have had in this EV space. But I wanted to also tell you a little bit of background about who Toyota is and our footprint here in North America. So to kick things off, we have over 14 facilities here in North America, Canada, US, and Mexico. We are really proud that we have launched over 2 million electrified vehicles. And Toyota has a philosophy to build where our customers are. So 80% of the vehicles that we sell here in North America are actually made here as well. And I'm sure all of you watching the news and the press and podcasts, Toyota feels very strongly on our multi-pathway approach. And what that means is that we want to give our customers opportunities to drive our vehicles on a variety of powertrains. So of course, we are promoting our hybrid vehicles, plug-in hybrid, battery electric, fuel cell, and of course, ICE. Let me tell you a little bit more about that multi-pathway approach and some of the success that we've had in the past and success as we move into 2026 here. So I'm really proud to share that we have over 32 Toyota and Lexus electrified vehicles. And this year in 2026, we're launching 11 new ones. Maybe you've heard our most recent press release. Later this summer, we're gonna launch the BEV Highlander, one of our top selling vehicles. And then Lexus has announced that our goal is to be 100% electrified by 2035. I will tell you there are many, many challenges. And actually on the panel discussion, I think we're going to talk about some bottlenecks of the future. But affordability is one of Toyota's #1 priorities. And I'm sure you guys have seen the stats, but the average BEV costs around $59,000, while the average ICE costs around $50,000. And for our customers that can't afford that, Toyota's solution is that we have 11 models under $35,000, including the Corolla Hybrid. The sticker price is less than $25,000. So if you want a wonderful fuel economy at a compact vehicle price, the Corolla Hybrid is the way to go. Okay, telling you guys more about some excitement in North America. I am really excited to share that last year, we completed our $13.9 billion investment in North Carolina. Again, Toyota builds where we sell. We also wanted to be able to manufacture battery cells here in North America. And just last year, we lined off our first HEV cells. These are powering our Camry HEV, the Corolla Cross HEV, RAV4, and Highlander. And my team, my battery cell team, gets an opportunity to work very closely with this plant to make sure that we are successful in our journey to build cells here in North America. Because we are at the EVC and I'm a proud alumni of the University of Michigan, I also like to share what's going on in Michigan. And Toyota, you may not know, is located just 15 minutes from this campus. We have 2 facilities, one in Ann Arbor, one in Saline. Our Ann Arbor facility is where we're doing advanced research, powertrain design, materials engineering, and evaluation. And our Saline campus is where our design headquarters are, our chief engineers, and our supplier center. And what I'm super excited about is that our new battery lab will be coming online here this summer. And the focus is on cell, module, and pack performance and durability evaluations. And then finally, I think some of the previous speakers spoke about how important STEM outreach is for our future. I'm really proud to share that, part of Toyota's strategy in terms of growing our customer base and the excitement is the young students. So we have a STEM outreach initiative called Driving Possibilities. It's throughout North America. We invest heavily here in Southeast Michigan. And currently we are partnering with Ypsilanti Community Schools, MEDC, and the Washtenaw CTE programs. And we're bringing programs to the classroom like Curiosity to Career, where we have our battery engineers coming in and speaking to students about what it's like to be a battery engineer or to design a battery cell. And these students are excited to be a part of this growing EV ecosystem. So with that, I will close and pass it off to my next colleague. Thank you.
And now, please welcome to the stage, Mohamed Alamgir.
Thank you very much, and good afternoon. My name is Mohamed Alamgir, and I have worked with LG Chem or LG Energy Solution for the last 25 years, and I retired last year. And today I'm pinch hitting for my bosses who are traveling. They said, you go and present some of the materials we have. So if you have a difficult question, you can save it for them for the next sessions there. Anyway, I would like to start with giving you an update on LG Energy Solutions EV and ESS business. Some of you might know that LG Energy Solutions was spun off from LG Chemical in 2020. And the LG Chem is the largest chemical company in Korea there. So our battery business is divided into 3 segments: the automotive, and that encompasses anything related to transportation. And the next one is IT and mobility. That's for consumer electronics, power tools. And the third one is the ESS business. So that is for grid and business and residential one. Being a global company, we have locations around the globe. We have research and development center, as well as manufacturing sites across the globe. And lion's share is actually, interestingly, in the US. We have 7 plants in the US. And if you can see here, the bulk of the capacity of these manufacturing sites will be located in the US, and over 50% of the capacity is expected from the US there. Speaking of the US, we are actually in the US over a quarter century. So before the word gigafactory became a commonplace word, we started the gigafactory in Holland, Michigan in 2012, producing batteries for GM Volt, the first high-volume plug-in vehicle in the world. So we have a proud history of pioneering the onshoring of battery manufacturing to the US. Holland will be producing more than 20 gigawatts of capacity in 2026. Of course, we are in all segments of the battery manufacturing, starting from materials to cell, to module, to battery pack, as well as a BMS. And we all deal with all the chemistries, NMC, as well as LFP, and also cell formats. Pouch, we are the largest manufacturer of pouch in the world, as well as cylindrical or prismatics also, as you have noticed in the recent announcements there. Current focus for the company, as you have heard, being in the battery business is not the best times now. We are going through challenging times because of the current administration's policy. So it is a very difficult time for the battery suppliers. However, we are very fortunate that some of the new products are getting traction. Especially we are building on the volumes that we are getting in the ESS, as well as on the new products on the 46 series of cells there. Along with that, strengthening the portfolio for the current business, we are also trying to stabilize the North American operations. For example, many of the plants we have started are going through a hard time, so we are trying to utilize the capacity for other applications such as ESS. Also, we are trying to enhance the supply chain for the US to meet the US material need, as well as we are also focusing towards the next generation chemistries, especially the lithium metal type of chemistry as well, also for increasing the fast charge capability there. Speaking of the ESS, that has been the bright spot in this doldrums of battery business there. It is expected to have significant growth in the near future, especially driven by grid, renewables, as well as you always hear data center and AI expansion. And we have over 100 sites in the US that services the grid, the ESS systems, and we have over 16 gigawatt hours capacity, and this is going to significantly increase in the coming years there. And you can see various locations where we have our ESS sites. Speaking of that, these new businesses actually, or this new growth industries actually has opened up significant opportunities for localization, especially for ESS. For example, we can go into mechanical and electrical components sourcing in the US, as well as the cell components for LFP, like anode materials or electrolytes and foil components. Similar situation is also for the 46 series of cells there, where we can have cans, as well as anode materials, as well as the NMC cathode materials there. So these are the new opportunities that are available for any aspiring suppliers for the industry we deal with there. Okay, that would be for me a short update. Thank you very much.
And that, please welcome to the stage, Neil Dasgupta.
All right, great. Thanks so much for the opportunity to speak here. I'm Neil Dasgupta. I'm a professor here in the departments of mechanical engineering and material science and engineering. And I'll be giving you a little bit of a brief update, a little more technology focused here on solid state batteries, which is something I'm sure many of you have heard about. We even heard it mentioned today earlier in one of the panels, something I personally have been researching for about 13 years now. So I'll give you a little bit of a decades-long journey and perspective on where that tech is and where the challenges and opportunities lie. So first off, why are we at this sort of R&D university level interested in solid state battery technology? If you take a look at the cartoon shown here, you can see inside the battery the key critical components. Of course, the positive and negative electrodes, which are the cathode and anode respectively, as well as the separator, which in a lithium-ion battery contains a liquid electrolyte. And the key advance in the solid state battery technology is to replace that liquid with solid state materials. So what are some of the motivations and advantages of this? Well, probably the largest one is trying to enable a step increase in energy density. And that happens by replacing graphite, the current negative electrode material, with pure metallic lithium. You basically get rid of the host that's storing the lithium ions on the negative side, and you can reduce the volume and mass of the battery substantially. Another additional benefit of moving to solid state versus liquid electrolytes is that the primary flammable component, or the most easily ignitable component in the battery, is the organic solvent used in the liquid electrolyte. So if you can replace that with non-flammable components such as ceramic-based separators, you could potentially improve battery safety. And then finally, you have the opportunity to have more of a physical layer that blocks crossover between the two electrodes. We like to think of batteries as these separate positive and negative sides, but many battery chemistries, you have things dissolving on one side that might migrate to the other side of the cell, and that can cause problems. That becomes more of an issue if you start looking at next generation technologies like, say, lithium sulfur cells, where sulfur dissolution and crosstalk is a big challenge. Okay, so those are the motivations, but why don't we have solid state batteries today? This was a cartoon we drew from a perspective article that I wrote with a close colleague and collaborator, Jeff Sakamoto, a few years back, where we summarized some of the both fundamental and applied engineering challenges that are really limiting solid state battery commercialization right now. You can see on the left-hand side things like mechanical properties. I'm a mechanical engineer. There's a lot of interesting mechanics within a solid state system. You take a liquid that can flow easily and wets over surfaces and replace it with a solid. Now you have these mechanical stresses and strains that can lead to fracture and degradation. Thermal properties, how well do these cells operate at elevated temperatures as well as low temperatures? And a lot of the times this comes down to understanding the interfaces within the battery. It's not just the materials themselves, but what happens when you pair them and mate them against each other? What are the phenomena at these interfaces? Can you operate these under a wide range of operating conditions? And finally, as I'll touch on in the end, manufacturing and manufacturability becomes a key challenge. Dealing with very thin sheets of solid electrolytes, how do you make them so that they don't crack or have pinholes? How do you laminate them and integrate them into cells? These are some of the challenges that the industry is heavily focused on. So here at the university, we look at those sort of application challenges and translate them over to the scientific challenges. And these are some of the things that the EV Center projects and batteries are taking a look at. So for example, on the left-hand side of this slide, you can see in this solid state lithium metal battery, what are some of the underlying causes? What are the things that really cause problems? This could lead to things like physical point contacts at solid-solid interfaces, the fact that you have large volume changes. If you're replacing graphite, which doesn't swell that much, with lithium metal, which swells quite a lot, this creates lots of volume change that then manifests itself in fracture or other degradation processes, as well as things associated with the manufacture of porosity, defects, scratches, etc. How well and how perfect can we make these batteries? And can you do that roll to roll at a meter per second web speed, targeting less than $100 a kilowatt hour? That poses a lot of manufacturing challenges. Perhaps the sort of reach goal, or maybe the holy grail in pretty much all lithium battery technologies, is moving towards what we would call an anode-free configuration. In this case, we actually completely eliminate the excess lithium metal on the anode side of the battery, and all of the lithium inventory within the cell. That tells you, basically that maps to the capacity of your cell, which maps to the driving range of your electric vehicle, comes from the cathode. And you can see on the right-hand side, the design challenges there. If you want to enable a battery that is truly anode-free with 0% excess lithium in it, you need your Coulombic efficiency, in other words, the percentage of how much charge you get back versus how much charge you put in, to be 99.98%. Lithium-ion batteries currently can do that, but that's one of the most remarkable things about lithium-ion battery technology, right? Intercalation chemistry won the Nobel Prize in 2019 for a reason. It's really hard to do that when you're talking about plating and stripping lithium metal in the cell. So those are the challenges. What are some of the sort of solutions? Again, I'm just giving a bird's eye view here. A lot of it comes down to interface engineering and interlayers. You can see here a range of different types of thin films. And when I talk about thin, it might be as thin as like microns or even nanometer scale coatings. So there's been a range of reports recently on looking at, for example, alloying elements. You add a little bit of silver or gold. Well, they improve things, but they also are expensive metals. Could you use something like tin, for example? Samsung had this seminal work showing carbon interlayers can be inserted. And what are you trying to do there? A lot of it is trying to prevent delamination and contact loss inside the battery. But the mechanisms are still partially unclear. And then even if you do understand how they work, are you going to be able to manufacture this in a scalable roll-to-roll process? So taking a look at kind of like the system level of the entire battery here, you can see that in order to achieve the stated energy density targets, you oftentimes read things saying, hey, solid state batteries could give me 1,000 watt hours per liter. You see that, yes, that is possible, but you have some pretty stringent design requirements on how thick is the loading of your cathode material, what is the percentage of active material within that layer. Companies like LG understand this well. That's what's pushed lithium-ion batteries over the last 30 years to higher and higher energy densities. It's not like we found some magic material that works twice as well as the original materials developed back in the 1980s. It's just that the manufacturing advances have enabled us to go thicker and thicker and reduce the porosity to lower and lower while still maintaining good performance. Doing that in a solid state system is challenging. Then once you've got your battery cell figured out, you need to start thinking about the packaging and the fixturing requirements. And one of the big challenges for solid state batteries is the requirement to apply a stack pressure. You take a battery, you cut the size in half, you reduce the weight, but all of a sudden, if you need thick metal plates to physically apply pressure to compress these materials together, that counteracts a lot of those benefits. And so, at the laboratory scale, we make these little fixtures that are bulky objects, but thinking about how does a vehicle manufacturer integrate that into a pack without, sacrificing weight and volume is a big challenge. So, we interviewed various different automotive OEMs, and the consensus was you need to get the stack pressure below about 1 megapascal of pressure, and that's perhaps doable without major challenges, but current solid-state batteries oftentimes require 5 or 10 times as much pressure as that. And why is that pressure important? Well, you can see from this cartoon, again, without getting into too many of the details, a lot of it has to do with the fact that you replace a liquid that can flow and wet a surface, so it's a conformal, uniform interface with these solid point contacts, and you really have to push on them and squeeze them to get them to mate together and transfer lithium ions across. So this cell shows that, for example, if you go from, say, 1 megapascal to 17 megapascals, you have significant differences in terms of the first formation efficiency of your battery, as well as the power, not just the energy, of how fast can you charge and discharge these cells. So those same energy power trade-offs you get in lithium ion, you have a different set of physics and requirements and engineering in these solid state systems. Another thing I want to emphasize in the manufacturing is the importance of coatings. So if you're trying to take these two solid materials and mate them together and they just don't like to do that, well, the first level solution is, could I find a coating that makes the interface better? But then from the manufacturing standpoint, it's like, how do I do scalable coating of these thin film modifications? If I'm using solution processing, like you can see in this cartoon, you get these polycrystalline materials with defects and grain boundaries. Really what you want is something very thin and conformal and perhaps amorphous without these crystallographic defects. This is where techniques like atomic layer deposition, being commercialized by companies like Forge Nano, is scaling it up. And we're already doing this on NMC cathodes. cathodes to enable nickel-rich chemistries, but there's a different set of coating processes and materials that are going to be necessary for solid-state systems. Shown here is some recent research work from our group where we demonstrated that this niobium oxide coating on NMC could enable very efficient first cycle reversibility in these cells, even up to 4.7 volts. And because energy is the product of charge and voltage, anything you can do to boost the voltage while maintaining stability is going to be important. Finally, just last things I want to mention is how are you going to manufacture these things? This is something the EV Center is looking at actively. You have these wet processes like slurry-based coating. That's how we currently make lithium-ion batteries. Can you do that with solid-state components? What's the chemistry of the solvent? Is it going to change the nature of the material? We're also looking into dry-based processes, just like you hear about for lithium-ion cathodes, but then get into challenges of what's the binder, how much of it do you need? You have delamination and cracking issues, et cetera. Then once you figure out how to coat them, you got to layer them together. So integration and lamination is a big challenge. Samsung, for example, reported using warm isostatic pressing, which can really densify these materials very well. But is that a scalable technology? Can you do that at low cost and high throughput? The challenges remain there. And finally, I want to mention, all these material science and manufacturing things I'm mentioning. That's kind of where a lot of the research is at. But there's this whole forefront of once you figure out all those challenges in terms of integration of these cells into the vehicle, what about diagnostics, state of health monitoring, battery management systems for solid state batteries? We really need a lot more sort of understanding. So there's challenges, but there's opportunities there. I want to show one research advance in collaboration with Katsuo Thornton's group here at Michigan, as well as Jeff Sakamoto. We demonstrated that taking something like impedance spectroscopy, which is used in the lab, you apply this AC high frequency perturbation to your cell and you can diagnose it. We demonstrated a very simple strategy where just a single frequency AC perturbation could be used to diagnose contact loss and degradation of these solid state batteries very early in the cycling. So with that, I'd like to acknowledge the research group, collaborators across the university, EVC, and thank you for your attention.
As Faye and Mohamed join Neil on stage, please welcome Nick Kotov, the moderator of the panel.
Good afternoon. I would like to say a lot of thanks to you all for participating in this event. I will open the panel just by a couple of remarks. I'm Nick Kotov. I'm a professor at material science and chemical engineering. I work on a number of topics. The key is the battery. I also had started 3 companies in this space, 2 on separators, 1 on lightweight composites. And also, University of Michigan now is a house of the NSF Center for Complex Particle Systems, which develops the fundamental science for cathodes, anodes, and separators, and a lot of proprietary technologies. I would also like to say that this is an opportunity to thank a lot of our collaborators from industry in the thrust that I'm leading with Wellen, and this is General Motors, Thermo Fisher, BASF, Dow Chemicals, and LG. I also would like to point out that this event and the center itself is actually not just another center. It's a paradigm change, how academia and industry interact. And you feel it already. It's very important for, I think, each side to understand better each other's metrics and language, and the participation of industry in the project intimately change the dynamics and outcome of what we have done. And this is very valuable for every person involved. And Faye had mentioned STEM. And in this space, I would like also to say that this paradigm change also also involves the changing of mindset, both for academia and industry, and also changes what are how the students that we involve in the work are educated. It's not enough nowadays to be skillful in just synthesis or some process that you know. It also needs, you need to understand both the chemistry and the stock market. You need to understand the microscopy and what the projections for ROI is. And with that, I'd like to open the discussion in the center, which will be directly in around this current developments in these interactions and the future needs for the collaboration. And I would like to first open with a question to all the participants of this panel. So the transition of EVs from hype to acceptance have been very noticeable. What kind of past advances you see as pivotal, essential for that to happen? And I open the discussion for everybody who would like to start. Maybe Faye.
I get to go first. Thank you for that question. I think I'd like to give a little history lesson, if it's okay, the Toyota history lesson. You know, we are making great progress with EVs here today, but in 1997, it was when Toyota launched our hybrid Prius. And I think we all think back to 1997, that feels so long ago. Next year is gonna be 30 years that Prius has been on the road with over 1.5 million sales. So I think that breakthrough technology back then, and the more customers see hybrids, BEVs, PHEVs, FCs on the road, it makes the acceptance easier and easier. And I think it's in the area of safety, trust, affordability, and these are all things that will help us move forward in the future.
Thank you, Faye. Neil.
Yeah, a lot of things to consider there, but I think that as we think about the next generation and looking forward, we really look to companies in industry to take risk and be willing to, invest in research, but also realize that sometimes you need to lose money for a while before you can start making it. I mean, I remember sitting at a dinner at Stanford in 2005 with this person talking about this company. It turned out to be J.B. Straubel, became CTO of Tesla at that time in 2005, right when the early Model S came out. And you look at the price of lithium-ion batteries back then, 20 years ago, versus now, and they've dropped 95% in price. But being a company early on that was willing to sort of do the engineering development with that recognition of the future potential for price decreases and recognizing that economies of scale and manufacturing and a little bit of luck all need to come together. But I think that if we don't do that here in the US EV auto system, we're going to fall way behind because we're seeing that happening globally. So I think it takes vision, it takes risk, it takes willingness to, survive that valley of death of financial cost to get to that point. But, if we do that, we could really transform the industry.
Thank you, Neil. Mohamed.
So, can you hear me?
Excellent.
Actually, they covered most of the key points, but I have been in the industry for 40 years. So, if I started in '84, and at the time, lithium metal was the topic. There was a lithium metal, and lithium titanium sulfate was the system there. And if you know the history after that, it is amazing how the field has developed. There was a company called Moly in Vancouver that had the first lithium molybdenum sulfide battery, which went into NEC phone in Japan, and it caught fire in somebody's ear, and the company went bankrupt. So I was in Boston in an R&D company working also on lithium metal batteries there. We were working on lithium titanium disulfide, and my company's CEO, it was a privately held company, and he said, no, this is too dangerous. I don't want to lose my company. Anyway, so we were developing electrolytes. So the big question we had always, can we make the lithium rechargeable batteries at that time there? So big advance, what you meant was, to me, the biggest advancement was the introduction of the carbon, along with that, intercalation cathode, the carbon introduction of the graphite anode changed the whole world. We did not know about that part as yet. So that was the tremendous advancement with respect to the introduction of these lithium batteries at the time there.
Exactly right. And in my mind, that actually underscores very nicely the need for the development of new materials. And sometimes one material looks very good, but eventually some unfortunate event like this happens, and then you got to develop something else. With that in mind, let's evaluate maybe some challenges that are ahead, and we've heard a few. Faye, if you could possibly share some of your thoughts from the perspective of Toyota about the challenges and bottlenecks.
I get to go first again. But Neil, earlier you talked about taking risk and a loss, and I agree, we lost money on those early sales of the Prius, so I think it's great that you brought that up. Okay, bottlenecks. Okay, what do we talk about? Should we talk about critical minerals? Should we talk about charging infrastructure?
All of the above.
Should we talk about affordability? Oh my goodness, there's so many to choose. You know, what's heavy on my mind right now, I mentioned earlier in my presentation that Toyota just launched our North Carolina manufacturing facility where we're producing HEV, BEV, and PHEV battery cells. And anytime you're launching a new facility, we know there's startup challenges. And what's heavy on my mind is following the Toyota way, the Toyota production system, continuous improvement, and Kaizen. And really what we're trying to do is bring the cost of that battery cell down. Because we talked about the cost of these cells are extremely expensive. We've talked about earlier presentations that the battery is the most expensive component of the vehicle now. So we really need to bring the cost of those cells down. And early in launch, we have fixed technology today. So really we're looking at manufacturing efficiency improvements. After the manufacturing efficiency improvements, then we'll move on to the new technology that our researchers are working on to continue to drive that cost down. So I think that's what's heavy on my mind right now is driving down the cost of cells through efficiency.
Makes a lot of sense on my side as a customer.
You can drive the Corolla Cross though, it's $25,000. Okay.
I will be happy to do that. I'm actually I'm looking for an opportunity. I think that view in the future can be informed some view of successes in the past. And my next question is to Mohamed. So you have been in lithium batteries for, I think, 40 years in LG. In different capacities, and you held the principal positions there. What are the things that worked well? What are the things that actually catalyzed that transition in well-working lithium-ion batteries now?
Yeah, like I mentioned, I started with lithium metal. Then I moved into, so of course, when Sony started that, the lithium-ion battery system, we also moved on to lithium-ion batteries, and I actually started with cell phone batteries. And lo and behold, we are actually selling to LG Electronics in '97. So America sending batteries to Korea. It just happens the other way around now, right? So. But the main thing was, like I mentioned earlier, the advancement that allowed this work to continue was was this, introduction of this intercalation cathode anode. But from the lithium ion side, when we switched to large batteries for EVs or PHEVs or HEVs, we formed this small company in Colorado Springs, the prelude to LG Energy Solution. We started in Colorado Springs. We were like 5-6 people there. And then this was actually, following up on Faye's statement, 97. That's when it started, 97?
1997.
97. So I think we formed the company in 2000. So we went to the automotive OEMs. So our company was formed in Colorado. We went to GM, Chrysler, and Ford. They said, forget it. Don't come near us now. We are making tons of money. And Hummer was humming at the time, big time, right? So I said, oh my God, we started this company. We have no business there. So the big challenge was to convince these guys to, that you can manufacture lithium-ion batteries also for EVs. And there was a big symposium, Advanced Automotive, I don't know, Menachem Anderman had a battery symposium. I forget the name, it's called. In 1992, there was 2002 in Las Vegas, there was a battery meeting, and they said, no hope ever for lithium-ion to be in EVs. It will be nickel metal hydride like Toyota does, right? So we all came out depressed. I said, oh my God, if Menachem says this one, we are in trouble there. So the big breakthrough happened with NMCs and carbons, and we started making cells for HEVs and PHEVs. That made the history there. So that was the big breakthrough. We're having the NMC cathode move away from cobalt oxide and make, we started with blend of NMC and spinel for the GM Volt. So that enabled the switching to large batteries, large cells that will survive the safety test and also give you enough power and cycle life. And also the range GM was looking for, a 40-mile range on a plug-in hybrid. That enabled the whole thing,
That's a very nice example of the technology development. And thinking of that, it actually brings up some thoughts and some words I've heard when I give the pitch to some investors for the small companies. You always hear, oh no, it will never work. And in 3 years, it does work. And with that thought in mind, Neil, I think not everybody knows that the University of Michigan is a home for a major investment from the Department of Energy on solid-state batteries, and you're the head of it. So if you give us your perspective, perhaps next 5 years, what are the biggest events that you anticipate there?
Sure. I think that something I've come to realize, having worked on next generation batteries for a while now, is that lithium-ion batteries are not going away. They're not going away anytime soon. They're not going to decrease their demand. So when we think about a next generation technology, we need to stop thinking about it as the replacement and instead as the augmentation and opening up new possibilities and new market segments that may be still out of reach for lithium-ion. For example, electric aviation is one you hear a lot about, but also non-flammable batteries for defense applications is one. I think that there's still as an EV driver myself, the two biggest bottlenecks I see for electric vehicles, and similar to what we heard today, once I bought my first one, I'd never go back still, but is low temperature performance and fast charge, right? I mean, those are still the two biggest pain points we hear from the industry. It takes 3 to 4 minutes to refuel your gasoline vehicle. And if you look at the enthalpy of combustion of gas, that's a megawatt of power you're putting in. So whether you're talking about 100 kilowatts or 200 kilowatts, you're still talking about an order of magnitude difference there. So could you enable that type of power density? If so, then you could start to really, enable some new applications. And then the low temperature thing, I think, is still a really big pain point. You buy your electric car, it's rated at 300 miles range, but how does it perform in February? And, this is something I actually get, emails every year from the Associated Press of, oh, why are these cars lining up at the level 3 chargers in February? And the first thing I said to them was, well, they should have, preheated their battery. But it does take some planning, and you don't always have the opportunity to plan. What about 2 a.m. when your kid is sick and you got to get to the emergency room and your car needs charge? I mean, those are the human situations that we're dealing with. So I think that the next gen batteries need to be able to solve those types of pain points that lithium ion reaches some of its fundamental limits. And so again, I don't see it as replacing lithium ion, but if successful, they could open up those new types of market segments.
Excellent. I think this also informs the academic side. I think in academia, we often think about different metrics and we forget the human side of the technology. And with that kind of mindset and understanding the new dynamics that we're establishing here, Faye, Mohamed, I'd like to ask you, what from your perspective is still missing from the interactions between academia and industry, the researchers who actually make things and think of things, if you don't mind. So what we need to do more and what we need to do less in academia?
Should I go first?
Absolutely.
What to do more of and what to do less of. Actually, I want to answer the question with more of how great the EBC is collaborating with industry. So I'm going to kind of pivot that question a little bit. Toyota right now is working on 4 key projects with the EBC right now, and I think it's going quite well. Really appreciate this opportunity where industry is able to partner with the professors. Actually, Neil is one of our colleagues that we're working with one of the project themes on. I think in addition to the research projects, the EBC is also focused on the workforce development piece, and I spoke about workforce development in my presentation, really exciting the next generation. But one of the key things that I learned in our advisory board meeting is the great progress the university has made on their master's programs for the battery manufacturing programs. And I think that those master programs are really critical to our future engineering workforce. One thing that we didn't talk about is our technician workforce. I also lead quite a few technicians within my own organization and readying that workforce for the next generation. So actually to do that, we're working very closely with Washtenaw Community College, which is just, stone throw away from the campus here. And through their FAME program, it's a 2-year apprenticeship program where we're able to develop those next generation of technicians. So to kind of wrap it all up, I think let's keep doing what we're doing. The EBC is doing all the right things to have industry collaborate with academia to drive forward EV research and education. It's okay?
Fantastic. That's a very strong endorsement.
Yes.
Mohamed.
I have little input to this one. So as I said, I'm an old man. So when I studied in Boston, I was part of the ECS local section. So one time I think I invited, I don't know whether Mark Wrighton is still active. So we invited, he was an MIT electrochemistry professor. And I think he later on he became Washington University president. Anyway, so he was invited and he was giving a talk. And got to talk about it. And he said, oh, you guys do batteries. Who does batteries? This is an MIT professor. This is 1985, 86 timeframe. And look at you guys now. Every professor in University of Michigan, somehow or other, involved with batteries or materials or characterizations or safety or whatever. This is just beyond me and unthinkable where I have seen the industry. At that, I don't think in the 80s anybody worked. Maybe there was a group at Stanford, I forget somebody's name there. He was a material scientist. But it's unthinkable where you guys are there. So this is fantastic. And I do agree with Faye, the technician, or in Germany they have what is called learning. And I don't know what is the equivalent word.
It's called apprentice.
Apprentice. I know the German word. So I studied in Germany. Anyway, so this is unthinkable where we are now. So this is fantastic. And what EVC is doing, it is, again, just beyond my comprehension.
Thank you all, and let's give our panelists a big round of applause. Good thought.